No, I haven't yet. I TA'd it once. And I've tutored it a crap ton. Like I spent most of my undergrad tutoring and then like years on and off tutoring here and there. Um, but yeah, I just haven't had the chance to teach it yet. I got cycled into a grant in 1073. Did I hit record? Yes, cool. That's fine. Um, which is our college algebra for STEM majors. And then when that grant finished, I ended up starting 1093 pre-cal. I did that in the spring, and then in the fall, I got assigned to this class a week before classes started. So like up until then, I didn't have a third class. I was like, am I only gonna have two? That'd be really nice. I could do so much. Poof, teach calculus. It's not the calculus part that's bad. It's the you have 1 week notice to come up with notes and the syllabus and everything. So that's why I've been stealing Chris's notes the entire semester. But this does segue nicely into what time of year it is. It is course evaluation time. So you guys should have started getting the emails with the links. Um, Let me explain a bit how course evaluations work in college. So one, they're not like the fast food surveys you may have done for friends where they're like, just give me all perfects because they get in trouble if they don't get all perfects. These are not like that. So if you guys gave me like straight 4s out of 5 across the board, that'd be fine. If you gave me some mix, whatever. Like my averages have been higher than the department's, which is fine by me. Um, and the department on the whole isn't too bad. So the course evaluations are the chance for you to tell your professor what you like that they do, what you don't like that they do, or something that they don't do that you think would be helpful. Um, the results from the course evaluation at the end of the semester are held hostage. We don't see them until grades are put in, finalized, done. So nobody is even going to look at those until probably January. Like they don't even send us the email right away. It takes forever. So I say this because if you have a professor that's doing a bunch of stuff that's really bad and you're worried about telling them and them retaliating with your grade, we set the system up so they can't do that. Uh, but the other qualifier with telling a professor what they do that's bad, um, like when we read evaluations, it's kind of like reading the reviews on a Google restaurant or on Rate My Professor, where you're like reading and everybody's kind of on the same page. And then there's this one person who's like, oh my God, it was awful. And you're like, you work at the restaurant across the street, don't you? Like, did you even go in? So with student evals, and I'll rate my professor, like there's some students who show up twice, ghost us the entire semester, and then email during finals week saying, what can I do to pick up my grade? Go back in time? I mean, like if you missed, two of the three tests and you didn't email to the end of the semester, unless it's to say, I just woke up from a 4-month coma, there's not much we can do. But sometimes those students get butthurt and they go rake the professor over the coals. So any review, you always kind of have to ask yourself, why is this person putting this out there? Is this the kind of person who didn't put forward any effort and now they're complaining because they're reaping what they sowed? Or does it sound more like the type of student who actually was trying, was going to office hours, was asking questions, and the professor just continually shut them down, like ignored them? So like that's how to read them, but that's also like how to write them. You don't want to sound like the student who never came to class and is like, this professor sucks. Um, so like when you write a review more than your professor reads it as well, it goes to the department. So if you are like saying this professor did this thing that was really awful, like try to provide some context details because the person reading it may not be in the class, they may not know all the details. Um, The other catch is if the professor is tenured, getting them fired requires a lot. So it probably won't happen just from bad student reviews.
It's like, with the reviews, this is the department they offer you to.
Mhm.
For me, I have a problem with the teacher, they put their heart and we're all like, yeah, it's better.
Well, that one, I think maybe like the student ombudsman person or maybe even like the provost of faculty affairs, like, because when it's the department level, it's like the chair and then how the chair is managing the department, although sometimes there's a faction within the department that's just making everything a pain. It's hard to say. The politics are as confusing as they are for cats.
We get extra credit if we do the course evaluation.
Yes, I will drop an extra web work grade if you do the course eval. So I don't see your results, but I can get a list of who did it. So, yes, I am totally on board with bribing people to give us more data. Because the more people that respond to a survey, like the better a feel you get for is this accurate? You know, it's looking at the Google reviews and there's only 3, looking at the Google reviews and there's 20, like, okay. Either 20 people felt this place really sucked or 20 people thought this place was okay. Cool. Yeah. So that's my like rundown on course evals, because I've had, like, I actually had a student tell me, I thought we were supposed to give you all perfect so you didn't get in trouble. And I was like, what? I was like, well, my friend at Whataburger. Oh, no, it's not like that. Be honest. If there's something I don't do that you think I should do, or something that I suck at that I can do better on, like put in bonus points when I should, and grade papers faster. In my defense, the writing assignments are not me, that's our TA, and he got sick, so he is very behind. And we are section number 18, so we're probably the last one. Okay. So a whole lot of extra information, but it does give you a little more context to how some of college works. All right. So now we're going to take a look at antiderivatives. So it is exactly what it sounds like. So consider this function 3x squared. Can you think of a function that after we take the derivative, the result is 3x squared?
Where?
There. So let's think about, like, if we have x squared, what's the derivative of that? Yep. All right, so x squared is not the function whose derivative is x squared. So what about x cubed? Derivative of x cubed is 3x squared. All right, so we've been looking at the down direction, if you will. Now what we're going to start doing is think about how do we go backwards. So we spent almost an entire semester learning one direction. We're going to look a little bit at the opposite direction, and then you spend most of Cal 2 doing integrals. And then at the very end, they introduce sequences and series, and everybody gripes and complains because it's miserable. And they're not wrong, it is. It's a whole lot of esoteric rules with not as much obvious meaning behind it, but strangely enough is like the one section that actually can be applied a lot more than people realize. All right, so let's think about the function x to the n. So when I have my function x to the n, when I do the derivative, my power rule, I bring down the power, and then I take one away from the power. So now we want to think about, all right, if I'm gonna undo this process, if I'm gonna do it backwards, figure out what function has the derivative of x to the n. Hold on. Let me change color. So instead of n minus 1, it's going to be n plus 1. And so we did power down, then minus 1. So socks and shoes, we also have to reverse the order. So we add 1, and then instead of bringing it down and multiplying, we're going to divide by it. So if I did the derivative of this, I brought down my n plus 1, it canceled the n plus 1. And then when I take away the 1, I just have x to the n. So now that we're learning about antiderivatives, one of the easy mistakes to make is to forget which way you're going. So I would actually write like crap like this at the top of my paper to be like x to the n derivative is this, and label it with a D. And then I'd be like, integral is this. Because this is the math symbol for integration, which is what antiderivatives end up being. So formal definition. A function f is an antiderivative of the function f if capital F prime of x equals f of x for all x in the domain of little f. Yes, thank you for a confusing definition. But basically what it says is if you take the derivative of the antiderivative and you get back what you were supposed to, congrats, you found an antiderivative. Now with this idea though comes a kind of weird thing. So these two graphs, like what's different between the two versus what's the same? The y-intercept is different. We got this one going through -2 versus this one going through 5. All right, what about the slopes of the graph?
It's just that one thing is transposed.
Yep. So the one on the left is lower, the one on the right is higher, but otherwise they're the same graph. So if I took the derivative of these, the slope at any particular x value of each of these graphs, because they are aligned, like our max in the middle, there's that -2. Our min over here is oh, that's not -2, that's -0.4, whatever. You know, our min down here is a little past -1, our min a little past -1, the other min somewhere over here, somewhere over here. So all our dips and peaks are all in the same spots. So when I take the derivative, it's going to hit 0 at the same x values. It's going to be increasing in the same intervals, decreasing in the same intervals, and at the same rates. The derivatives of these two graphs are equal, but the functions themselves are very different. The difference, though, is what we call an arbitrary constant. One of them is literally just vertically shifted from the other. So when we find an antiderivative, we're finding like here's the overall shape, but we can't pin down exactly where the graph is without some extra information. But for sure, I can still tell you this is the shape it makes. And we can still use it in a lot of interesting ways. So more fancy, but the whole point of this is to bring up this plus c. So anytime you're doing a general antiderivative, you figure out the formula like normal, and then at the end you just write plus c. So that's why the meme at the start of this was taking a math test and doing an antiderivative, slap the plus c button. All right. So we got one to practice on here. So it's got little f here, and then it's got big F is what we're finding. So that's the math notation typically used for the antiderivative. All right, so remember, derivative, the power comes down, so I'm doing the opposite. So my 3/2 is gonna stay. I'm gonna add 1. And then divide by that thing I just made. Minus x to the 12th. I'm gonna add 1 and divide by what I just made. Plus 10x to the 11th. Add 1 to the power and divide by that thing I just did. So this becomes x to the 3rd, and it's divided by 3. So my divided by, I'm going to write it out front. So that is a 1/3 times the 3/2. And it is now x to the 3rd. The 3's there are going to cancel, so it's just going to be 1/2 x to the 3rd. Minus, so this divide by 13, I'm just going to write it as a little fraction up front. 1/13 of x to the 13 plus, this is 10 over 12, and it's x to the 12th. And then the 10 over 12 can be reduced to 5/6. So we have the 1/2 x cubed minus 1/13 x to the 13th plus 5/6 x to the 12th plus c. So I looked over the web work. The web work on every one of these problems says your answer should include an arbitrary constant. So it gives you a reminder, put the plus c. This is what big F of x is. So you want to get practice enough that this makes sense, but you also want to make sure to focus your practice so when you go to do derivatives later, you don't mistake one for the other. Like, especially with a break in between continuing the topics, like that really is the number one mistake a lot of students struggle with in Cal 2. All right. Well, now we got one that's a little uglier. So what I do sometimes on these, like when I'm trying to remember, like how would the derivative work or how would the antiderivative work? I actually take the derivative. All right, so if I was doing the derivative of cosine of negative 11x, it would be negative sine of negative 11x, and then it'd be times negative 11. That's our chain rule. That's the derivative of the inside. So when I come over here for my antiderivative, all right, that negative on the very outside is going to carry through. And the 9 is going to carry through. So all of our derivatives had the constant multiple rule. Any number that's just multiplied in front just carries through. So when we do the process backwards, it also carries through. We'll have that written a little later as like a official rule, but yeah. Right, so that one we're gonna have to think about when we got a constant, what was the thing before that gave us the constant as the derivative? All right. So I have a cosine there. I know the derivative was negative sine, so the antiderivative would be positive sine. When I did my derivative, the inside stayed the same. So on the antiderivative, what's inside will stay the same. Give me this. There, now it's not in the way. But then I multiplied by the derivative of the inside. So when I go backwards, instead of multiplying by that, I'm going to divide by that. So this is going to be divided by -11. So that way, if I took the derivative, the chain rule would cancel out that -11 that I'm putting on the bottom. So I was doing the derivative to kind of remember how the derivative would work, so I could abstract to how the antiderivative works. So like this is more like thought bubble. When we do a derivative of cosine of a thing, it's negative sine of the thing and then times the derivative of the inside. So when I do the antiderivative, I keep the inside the same, like the -11x didn't change between the two. But instead of multiplying by the derivative of the inside, I divide by the derivative of the inside. Now the formatting on this question, like they put these giant parentheses and a negative outside. I don't know why, but whatever, sure. We'll just carry it through like that. It just makes thinking through everything a little weird. All right. So now I've got that +9 and I've got to answer what function, like what do I have before that I get 9 as the result for the derivative? If I
9x.
have x to the 9th and I do the derivative of that, power comes down. All right, but what if I had 9x? What's the derivative of that? So when we just have these constants, they're just going to get whatever variable. Yep, so it'll be plus 9x. Yep, and then at the very end, plus c. Slap the C button. Now, just like with some of our more complicated derivatives, we could clean that up, but that answers the question, and WebWorks should take that. The big thing to watch out for is this stupid minus sign with the parentheses. Like, I probably should have just distributed the minus sign and then just done the problem instead of keeping those dumb parentheses. Most of the problems that Chris puts in his notes, though, are pulled out of the old WebWork. So the WebWork assignment, which if you know anyone who's taking 12-14, is the homework they still have. It's like twice as long and 3 times as ugly.
Do we always put +c?
Yes. Anytime you're doing the general antiderivative. Ready? Here's a weird one. 11 cosecant 12x cotangent 12x plus 3x. Well, I know how to deal with the plus 3x at least. Add 1 to the power and divide by that thing. I know there's a plus c. Now we got to figure out this trig crap. So this is where knowing your derivatives really starts to come into play. So I'm seeing cosecant and cotangent. So if we think back, the derivative of cosecant is negative cosecant cotangent. So the one I have here is not negative. So in order for my derivative to not be negative, it means the thing I started with had to be negative. So that way, when the derivative gave me a negative, they'd cancel each other out. Do it this way. All right, so the 11 is going to carry through. We're going to have the negative. Now over here, our formula just had an x. But because of our chain rule, we know any formula where there's an x, I can think of that as being an ugly thing, and then I just have to multiply by the derivative of ugly thing. So it's the same thing for our antiderivative. When we get these little internal, more complicated expressions, we're going to pattern match back to our derivative. So so the antiderivative of this is cosecant of 12x. But to get my derivative, and there's no times 12 in there, I have to account for that by undoing multiplying by 12. So I'm going to have a divided by 12. So if we cleaned this up a little, the negative times 11 over 12, we have negative 11 twelfths cosecant of 12x plus 3/2 x squared plus c. Can I explain why I divided by 12 again? All right, so if I was going to do the derivative of cosecant 12x, I'm going to shift the screen over. My formula tells me that the derivative format should be negative cosecant thing and cotangent thing, like multiplied together. But anytime our thing is not just an x, the chain rule comes into play. So on the derivative, I'd multiply by the derivative of 12x, which is 12. So when we do the antiderivative, to undo multiplying by 12, we have to divide by it. So I pattern matched the cosecant cotangent to being the derivative of cosecant. So that means they will have an antiderivative that has cosecant. But anytime the inside is more than just a simple x, we've got a potential chain rule involving there. And I'm sure there's better ways to explain it. Basically, as you study calculus, what you learn is the number you're multiplying by or dividing by, when it's just a number, like you can kind of change it out to make it whatever you want. Now, if that chain rule like was going to involve an x, things would get a lot uglier. And that's actually U substitution, which will be like the first thing you study in Cal 2. So here, like they are making some baby chain rules, I'm going to call them. I don't like the word baby here, but because the derivative of our inside is just a constant, so we just see that constant show up. Now, if the inside of that was like 12x plus pi, it'd still be the same thing, except it would say 12x plus pi for the inside of the trig function. So another way we ask the question of find the antiderivative, the symbol to do this thing is this swoopy tilty S thing that looks like the shape you see carved into a violin. So we call it an integral. And then what you are applying an integral to is the integrand. And then the variable is the variable of integration. So you remember when we were doing like implicit differentiation and we talked about what are we taking the derivative with respect to? That same idea comes into play for integrals, but you're really not going to see it play out until either Cal 3 or differential equations. So generally though, what you're gonna see is the function will have x's and then they're gonna write dx afterwards. That's our differential to tell us what the derivative was being taken with respect to. So when you do the antiderivative, that's the variable that you're focusing on. So here we get our properties, sum and differences and constant multiples, the same way we got for derivatives. Antiderivating a product rule or a quotient rule is like a horrible nightmare. Product rule it ends up being called integration by parts. And you can get some weird stuff to happen with that. And there are some professors who get all butthurt about the tabular method for solving those, which I do not understand, but okay. All right, so now we get this one. So I want you to imagine like flipping to the homework section, you see a whole bunch of antiderivative integral questions, and they all just look like a bunch of crazy formulas. This is why there are calculus cheat sheets that are just lists of derivatives. It's looking at problems like this where you're like, what the heck format is that one? It's a lot to memorize and it's very easy to confuse them, but it is good to have a basic familiarity. So this whole divide by a square root thing almost always comes back to some of our inverse trig stuff. In this case, the square root is 1 minus x squared. That's the exact same square root I see for arcsine of x. So the only extra parts here are that negative sign and that 12, both of which are constant multiples. So we can factor those out. And look at this as negative 12 times the integral of 1 over the square root of 1 minus x squared dx. And now that is literally the derivative of arcsine. So if I integrated both sides of this and moved the dx over, there's our integration formula. So the integral here is just arcsine, which is the old school way of saying inverse sine. And we just keep the negative 12 in front and slap on a plus c. But the homework will tell you on every single problem, put in the plus c. So if you're ever not sure, like just look on WebWork for the note. Most of the time though, if you put it in there and you didn't need it, it's okay. All right, we got 11 minutes yet left, and I did want to make sure we got to initial conditions in class. So I'm just going to skip that one that was there. So if big F prime of x equals 4x cubed, is there any way to know exactly what function f of x is? And notice the exactly that's been highlighted here. So our general antiderivative, this is the 4 was powered down, so I take my 3, add 1, it'd be x to the 4th, divide by 4, the 4's would cancel. So our function, our antiderivative is x to the 4th plus c. We don't know what the vertical shift is. So is there any way to exactly know? Not just off that information, but what if we also knew one extra piece of information, that f of 0 equals 5. So I have this generic shape of a graph and it gets shifted up or down c, I don't know how many. But now I tell you, oh, on that original graph, if you plug in 0, the function value is 5. Well, I got a formula up here for big F. I could plug 0 in. So f of 0 is 0 to the 4th plus c. but f of 0 is also 5. Zero to the fourth is 0. So this tells us c is 5. So from that, we can now definitively say, f of x is x to the fourth plus 5. So we call this an initial condition or an initial value. Initial because a lot of times the variable that we're actually looking at is time. And when time is 0, that's your start. Typically, when you conduct any sort of experiment, you know what everything is starting at. So we're going to do our antiderivative like normal with the plus c, but then whatever initial condition they gave us, we can use to solve for c. All right, so here we have a derivative that is a linear function. So the antiderivative of this should be some quadratic. So dy dx, I'm going to call that a y. Negative 24x to the first. I add 1 and divide by 1 plus 1. Then plus 7. So I can think of that as actually 7 times x to the 0. I add 1 to the power, I divide by that. That's another way to see where the x is coming from. So negative 24 divided by 2 is now negative 12. X squared plus 7x plus c. Our initial condition says when we put in 0 for the function values, which makes the negative 12x squared 0 and makes the 7x 0, we get 5. So it's like the easiest thing to observe and control in an experiment. It's also one of the easiest points to plug into a formula. So we're going to have a 5 for the y value. Negative 12 times 0 squared plus 7 times 0 plus c. So c is 5 here as well. So our original function is negative 12x squared plus 7x plus 5. We found c. The initial value is this extra point they gave us. Yep. So like the full problem stem would have been, given the following derivative, what is the original function that produces this derivative with the added knowledge that the y-intercept is 5? Are you kidding me? Somebody accidentally started the meeting that got canceled an hour and 15 minutes ago that I never even said I was going to go to. Right. We've got another initial value problem. This one has a trig function involved. But luckily, when we plug 0 into trig functions, they give us integer values out, a 0 or a 1. Dude, come on. And then I don't think I actually saw any of these on your homework, but this is the second derivative. So we can find the first derivative, and we have a piece of information about the first derivative. So we can find the constant there. Then we can find the antiderivative from that, and one more piece of information to find the other constant. So Sometimes the things you observe are not even like initial conditions about the function. It might be like the initial speed of something or the initial rate of change. We call it initial because it's when time is 0. So when you're like observing an experiment, you just arbitrarily say, okay, time starts now. We can do the same thing in a lot of functions. Like if we knew this is the generic shape, we're like, and I observed my pattern starting here. Oh, well, that's like the original shape, but shifted over left or right. Like the left and right just represents like where you started time. The graph was to show the plus C, that we didn't know what C could be. But if I knew what the y-intercept was, that would tell me which of the graphs was the actual original function, because that would pin it down. Yeah. And there's our summary slide with a very long, crazy thing. I don't know, because we're talking about the final, no. Because if you look at this, this is basically a list of all the derivatives. We're not going to give you this full list. We might give you like, if we ask a problem that required like some of the stupid ones, like if we give you a problem that requires a derivative or antiderivative of an inverse trig function, like we'll give you that. We won't give you the full list. But this is a good list for, I'm trying to figure out how my antiderivative, which one is it? Like this shows you the derivative and then it shows you the integral formula that's the reverse written of the derivatives. You might see one on your homework. I doubt it though. I think like, because for 12-13, we cut out like half of the word problem, the ugly problems. The downside is though, you actually benefit from getting more practice. So we're probably gonna like swing back and put some problems back in, just not ugly ones, hopefully. All right, let me go ahead and stop the recording, but I'll go back and record the other initial value problems and I'll post a video of that later today, hopefully.